Hi. Quite recently, we have done some measurements in a rather large building, 170 meters long and about 8 meters wide, 3 lamellas, and it's 10 floors, 7 floors. And we have measured structural borne noise from demolition in the cellar. And I demolished brick walls and porous concrete brick walls and some light walls and some tiles and so on. And 2 of the days they used a robot, a ton heavy robot with a jackhammer, smaller hydraulic jackhammer, and it was used for the more heavy work, walls and so on. In the analysis afterwards, I wanted to see how much of the sound does propagate in a floor slab that is 160 meters long and 8 meters wide. So I made several Odeon models, and at the P1 point there, that's the drop point, I use as a standard a 40 kilo hand manual drop, drop from a bench, which gives about 100 dBA or 95 dB in the room next, close to it. And then there are points at different distances from the source, and you get tables like this for this is the first 99 for the first, and then 90, 89 for the second, and so on. And then you can make a table out of it. And this is a room acoustics program. It's Odeon version 16, and it's not made for structural borne noise calculations like this, but we do it anyway. One of the things that I wanted to know and understand a little bit better is how does the reflections from the borders influence the response. And I only have a point calculations for the closest source there, but you can see their image sources for the first 2 reflections out there. And then we calculate, simulate propagation loss using the air losses. You can put in relative humidity here. It's 12%, which is at the maximum of absorption in air. And so I did calculations for several different configurations with different widths of the slab, from 8, 16, 32, 64, and then finally 300 meters, to see how the width of the slab influences the propagation and the sound levels along the slab. Or yeah, really it's the vibrations, but the vibration velocity and the sound pressure is sort of proportional. So and then I have I can find the Excel sheet. And first we will see the calculations, the different calculations. We have the zone level up here, calculate the zone level around 100 close to the source. This is at 3 meters, and then at 12 or 13, and then the double distance, double again, and then a little more. And we have a logarithmic scale here, and you have 4 meters width of the slab. You see that close to the source you get higher levels down, but it isn't much higher than the rest for the next positions upwards. And then 8 meters, 16, 32, 64, and finally 300 meters. And you see it when you have a very wide slab and a wall behind you close, which probably is more important, you get the lowest levels here. And then I tested with a little bit more rough concrete as the material, and those are the lowest at distance. So you get more losses over distance with a higher absorption of the concrete. And this is the same graph using linear scale, and you see there's a sort of a loss function going there. And then finally, I will show you the measurements we did. And it's a bit complicated here, but we have, these are day values for the demolition work measured at different distances from the source. And what I do here is that I calculate the distance in 3 dimensions and use the shortest distance in air length as the distance to the receiver. And I'll come back to that. The difference between what you get in 2 dimensions and in 3 dimensions is not large when you come at the larger distances. The open brown and orange positions here are background noise. You see here we are close to the background noise, and also here. But under 50 meters distance to the source area, we do have signals. And I've calculated regression lines for the sound versus distance as these 2 curves here. And yeah, I'm using a minimum value for a day, and then I use a full day value here, I think. And then we have the Odeon calculations for the slab. And the curve is in the same order of magnitude for the decay rate. This is about 20, 25 log distance. But the level is too high. If we adjust the level to the same region as the average response in that building, we get points lying very close to the regression line there. And that is kind of interesting. This might lead to a theorem on this theorem. maybe we can use information from one slab to predict what happens in a building, which is kind of not as expected. And this is a building carried by columns, and then the slabs dominate and the columns will transfer energy upwards. So that's one of the things I wanted to show you. And then one thing is the Odeon, but there is some traits in the modeling there that can be used for structural borne noise quite clearly. And I haven't calibrated the losses or anything. So I have a graph here. Maybe I'll show you another figure first to make it more clear. Is this the presentation? This is the presentation here. And I also use and have presented earlier a little bit using the classic vibration velocity loss in a plate. This is really for flanking noise calculations and so on, but I stretched the model to use it also for structural borne noise in a building in concrete. And the first term here is the geometrical loss, simply the energy loss you get from diminishing energy as the energy is traveling outwards from a point source. And then there's a term, additional term, linear in eta, which is the loss factor, and linear in distance, delta r, radius, and linear in frequency. The higher the frequency, the higher the propagation loss you get if the loss factor is the same. And then it's a bending wave speed as well under there. And as concrete plates are, they are dispersive, so the bending wave speed varies a little bit with the frequency. It increases with frequency, I think. And the critical frequency or the coincidence frequency for 200 millimeter concrete, as I use as an example here, is around 100 or 150 hertz. Maybe it's 200, I don't know, but around there. And above that, you have a good coupling between the concrete and the air, so it will radiate efficiently. Now, this is the geometrical loss plotted along a logarithmic scale here, and then you have the it's the sound level, or it could be the vibration level squared if you want to. Then we would have to shift the numbers here a little bit, 26 hertz decibels, I think, downwards. But the blue line at 100 hertz octave band is the geometrical loss, and the red one is the same octave band with the propagation loss included. And we use loss factors, measured loss factors, and it's average for plates that are freely supported in a building. Liasjö example giving, and white, quite old data, some of them, but still we use data that are realistic. At 2000 hertz, it's a bit lower, and this is the frequency response sort of for that 40 kilo manual dropped on concrete, and it has its maximum around 500, 400 hertz. And the green line there is the geometrical and propagation loss at 500 hertz. And the orange curve is the zoom. So when we go back to 100 hertz and we see around 10 meters from the source, we start to see a deviation between the geometrical loss and the total loss in that octave band. So from there on, the propagation loss is important for the prediction. And this is 20 hertz, and the curve, the spectrum we use is A-weighted. So in the low frequencies, it's diminished quite a bit. And this is an illustration of how the distance from the source can be calculated. In the slab, it's those three distances that are included. If you want to do it in 3 dimensions, you have 3 and 4 distances that are combined. You take the root of the squared sum of this, and then you get this one. And one thing that happens is that in a building with realistic dimensions, here the distance between the floors are a bit exaggerated in comparison to the distance between the width of the floor slab. What we get is that it isn't very large distance difference between the 3-dimensional and the 2-dimensional number there. So in an assessment using these curves or this function, you pretty much get the same when you get at larger distances. Remember that this is a logarithmic scale. Yeah, and what shall we see? We have these curves again in a different direction. This is for a freely spanning floor, and the geometrical loss. And then here we have the same situation with a floor on ground. And these are all data. So the losses to the ground was higher before we started to use thermal insulation. So I don't think we have this situation any longer, but at that time you would have very large losses already at the propagation losses already at 10 meters. You would maybe go into 5 meters to get comparable levels. So losses of the floor does matter a lot if it's high enough. And I found 2 years ago, I wrote this long thesis in Norwegian, unfortunately, but I found one article by Asakura, who have done finite difference time history calculations of structural borne vibrations in a building. And here you see the trend as the time goes, and it's almost, the speed is almost the same in the up and down direction as in the plane, I think. And he has calculated mobility levels, vibrations over force in 5 positions, and 2 different cases, I think, and then measurements. And I've copied these, and I get if I plot these as with the distance from the source, I get a function that is has a decaying form, a little bit lower losses here than in the data I showed earlier. Some is horizontal and some is vertical. So, but I don't know if it's mobility squared or not. If it's, and I don't know how that influences, but there's a decaying function, and I used for the distance, I used simply the shortest distance between the source and the receiver. And here is the data plotted into my logarithmic scale loss curves, and they line up pretty close to the standard measure loss factor curves. And for the vertical situation, the loss is a bit higher, and it seems to be more linear, but it's few points, so it's difficult to say. And I've done some calculations to try to figure out how to do calculations on this. We do in our as consultants, we have to do some assessments. If we do not have the ability to measure which is the best, we drop weights and then measure in the receiving floors above or next to. And here is another article I found. I think the authors are Chinese, and this is a building with slabs in the upper floors, and then it's columns in the lowest floors. It's a combined building, and in the lowest floors there are transformers, electrical transformers, and I think these are different possible positions for the transformer, and I think it's calculated values for the positions on the walls close to the windows here, and possibly its measurements. I'm not sure. It's 2 years ago since I saw this and went through this, but here the data are copied and compared to the model as I explained earlier, and there's a little bit higher losses there in high frequencies, and I think 100 Hertz is a dominating octave band. Yeah, so not super, but not all that far from. Maybe there's higher losses in the building than we have in the model here. And this is the combined plot of both these articles, and one is column supported, and one is column and slab supported. And then I come to measurements I've discussed earlier in a different presentation. The building I'm living in with slabs, and here we see the dropped. This is measured in the cellar, 30 kilo dropped on the floor, and then in my apartment 4 floors above, about 60 decibels, 65 decibels, and then on the mat, and we get down to 45-ish or something. Okay, what shall we show you next? Have been through? I have been playing a little bit with this distance thing, and what we see here is distance in a slab, 22 meters wide, and they are over 200 meters long, just to see what happens. And I have this is the upper one is for the 3D calculation up to a given floor. I can choose which, and then down here we have the floor slab in the lowest level, and the center is here. And this one is the difference between those two. And what we have here is, let me see, this is 2 floors, 3.5 meters high, tall, and the distance between the 3D situation and the 2D situation is largest, close to the source, 6 meters, and at 20 meters we are down to 1 meter, and that's a very small difference when it comes to the sound level. And I've calculated the sound levels down here. This is for the upper level, and then for the lower level, and then the difference between them. And the difference here is 5 to 6 decibels close to the source. But when you get 12 meters from, you're down to 1 decibel difference. And of course, it's not like this in reality, because the loss from first floor to the second floor is what we measure in difference is typically 13 decibel or something in a column supported building. And this is the situation we have done. Now we have 4 floors. Maybe I should go back to 2 floors and see what it is then. And 3.5 meters for each floor, and then here we get more difference, but it's mainly because I've included the loss from the first to the second floor, and then a smaller loss for the next floors. So for the 4-floor situation in my own building, 3 meters, maybe it's less, 2.8 meters. Then the difference is still highest close to the source, 27 decibels. When you're 10 meters out from it, the difference is 21 decibels, and then it declines very slowly. So yeah, this is playing around with numbers and colors. What I wanted to express here is a sort of a possible theorem that we can assess the noise level, structural board noise level in when you don't know anything else. You can use the distance in 3 dimensions, and then this function, and it will probably lead to maybe it becomes a sort of a conservative estimate then, but I think it could be a possible theorem that could be used. Yeah, and if we look at the measurement, and yeah, here we have the losses, the same loss curve as I showed last some time ago, and then I plotted in two of the Odeon results, and I haven't calibrated those to each other, so the Odeon results are a little bit higher, and I haven't calibrated the losses. This is just the raw data without doing anything, and it seems like we may need some more loss. I don't know. For the measurements, in the large building I was talking about, the coincidence there is pretty good. So there might be something here. Okay, thank you for now.